the power of your brain. It may appear to be a little bit science fiction, but it is the truth of this remarkable advancement of this breathtaking technology. And to give us the glimpse of this technology, we are now having Dr. Anuradha Saha. So it's just a formality to introduce her. Dr. Anuradha Saha is an accomplished assistant professor in the Department of Applied Electronics and Instrumentation Engineering at Netaji Subhash Engineering College, Kolkata, with a PhD in Electronics and Telecommunication Engineering from Jadavpur University. Her research focuses on human-computer interfacing, biomedical signal processing, antenna design, and artificial intelligence. Dr. Saha has contributed extensively to her field with numerous publications in high-impact journals, conferences, and book chapters. She has supervised several PhD theses and led significant collaborative research projects. Her dedication to academic excellence is also evident in her active involvement in organizing international conferences, seminars, and faculty development programs. A recipient of the UGC Junior Research Fellowship and recognized for her contributions to cognitive failure detection in driving, Dr. Saha is presently an executive member of IEEE Women in Engineering Kolkata section and continues to inspire her students and peers with her passion for innovation and research as an advisor of IEEE Women in Engineering Student Affinity Group. I would also like to add, she is a wonderful mother. She has the tendency to control her students and in a very effective way, and I strongly believe the presentation she's going to have will enlighten all of us. So with this confidence, I am just handing over the platform to you, Dr. Saha. Please.
Thank you so much, Dr. Pratyusha, for this warm and kind words. So, participants, we are now in the first session of our very own AICTE ATAL online FDP on innovative pedagogy with AI and ML. And obviously, we are going to give you an approach of modern intelligent predictive control. So first of all, I would like to know whether I am audible.
Yes, you are audible. Absolutely.
Okay, thank you
Yes,
so
you
much.
are audible.
Thank you. Thank you so much, sir. So I'm going to first share my screen. So is it visible?
Yes, it's
Yes,
visible. Visible.
Okay. 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 Thank you so much. So since this is the first session, and as a coordinator, I would like to give you first insight of what is AI ML and how this is going to be blended with brain-computer interfacing to actually control any kind of modern, intelligent, automated vehicle. So whenever we are hearing about this term, that is automated vehicle, then automatically we are very much excited about the automated car, because now there is a very much in trend that is automatic driving. So my topic of today's discussion is basically on this integrating brain computer interfaces for predicting driving safety systems for drivers who are experiencing any kind of cognitive failures. So in that very case, I would like to add a touch of fuzzy logic, which is a very much, one significant pillar of self-computing technique of artificial intelligence or machine learning approach. Actually, I am giving this kind of touch so that we can usually pick a very common problem, very day-to-day problem, and we can learn that how we can utilize this artificial intelligence or machine learning with the help of this, intelligent technique, so that we can actually, you know, protect our drivers from accidents. So, on this note, I'm going to share my first screen. That is, whenever we are talking about brain computer interfaces, so what we need to do is we need to first learn that what are the brain modules we have, with which actually what kind of functionalities we are actually accountable for. So if we are, everybody of us are very much familiar with this kind of, picture or diagram we have seen in class 11 or class 12 in the biology book. So basically our brain is combined of these kind of, lobes. So basically the major lobes are frontal lobe, motor cortex, sensory cortex, parietal lobes, occipital lobe, and temporal lobe. So if you can imagine our, whole brain, you can see that there are the segments, and each segment is responsible for certain cognitive functions. Like whenever I mean, the most of our participants also, we faculties also, are basically in academics. Some of them obviously are joined here from industry persons also, and there also they are busy with the, or they are involved in the recruitment process, and we faculties are very much, aware of taking exams of students, right? So we actually follow that they, when the students are in, time pressure, when these are 15 minutes left to complete the exam, so automatically the frontal lobe actually of the students are very much highly cognitive by executing certain problems, certain, solving complex problems, executing certain functions, organizing and problem solving, and also certain kind of emotional and behavioral control as well. So this is a certain kind of functionality of the frontal lobe. When we are coming to the motor movement, because we are talking about the cognitive failure detection of the drivers. So automatically, whenever a driver is driving a car, or whenever we are actually moving, we are in very much hurry. So basically, motor cortex is responsible for our movement. Now there is a coming in the sensory cortex that is based on the, sensation part regulation. We have the parietal lobe also, which is very, very important here in this, today's problem, where this parietal lobe is associated with the perception. Because whenever a driver drives a car in a dynamic environment, or she needs to perceive the change, the dynamic changes of the environment, the certain, coming of the certain arrival of the pedestrian in the front of his car or her car, sudden change in traffic light also. So automatically their perception, or and the cognition, I must say, must be very, very high whenever the driver is driving the car. So parietal lobe is basically making the sense of the world, the perception, and also there is a certain kind of lobe which is, responsible for arithmetic purpose, was some spelling purpose, because whenever we have had a kind of, brain injury in the parietal lobe, sometimes we face that we have a, a speech problem, speech related problem. So spelling, that is a very important role of the parietal lobe. Then automatically we come with, in a very, the most significant part, that is the vision. That is our vision, because we have to see first, right? We have to be so alert visually that we have to, follow the changes in the traffic lights, the sudden changes of the, sudden the, the reduction in the gap from the, uh, the car which is before of a particular concerned car. So automatically we have to be very, very visually alert. So occipital lobe takes the responsibility for this visual signal processing. Then coming to the temporal lobe, which is important for memory processing, which is for understanding, for language processing, for these part. So basically, when we segregate or when we, all these lobes and we actually accumulate all the lobes again, the main four lobes in the cerebrum becomes frontal lobe, parietal lobe, occipital lobe, and temporal lobe. So now when these brain modules are basically, understood by us, then now coming to our today's problem. We are actually running late today, so this is the first day, but automatically I would try my level best to basically give you the full idea of the problem and the solution and the approach using AI and ML. So what is the problem of today's? The today's problem is cognitive failure detection in driving. So if we look at this flow chart and if we just try to, relate to our daily problems or the real world problems, the real world scenario, we can very automatically, we can, relate that what is happening and what we are going to show you through this flow chart. Suppose a driver is driving a car. So this is our start position. Okay. I'm just taking 1 minute to ask, to pause actually, and to ask you whether my slide is visible and you are, you can hear me.
Yes,
Am I
you are
audible?
Yes, ma'am,
audible
it's
as well as
clearly
visible.
visible.
Yes, yes,
Okay.
yes.
Okay. Thank you so
The
much.
slide
Thank
is
you so much.
visible and also audible.
Thank you. Thank you so much. So this is the start position, right? So automatically the driver is driving a car. So whenever a driver is driving a car, just imagine what we actually face in real world, that a driver can have three kinds of failure. Three kinds of failure. What are those three kinds of failure? He may be, experiencing visual attention failure. That means the driver may miss the changes in the traffic signal light, right? Or the driver may miss that a sudden car is coming in the front of his car. So this is one type of failure which is called visual attention failure, or here we have incorporated this visual attention failure by VAF. Now, this coming to the second type of failure. That is what? Let's say the driver is visually alert. Okay. He have also seen the changes in the traffic light as well. But somehow he is late, a little bit late to plan his required motor actions. That means automatically, if I am a driver and I will see there is a traffic light changes, so automatically within a very stipulated time, will have to plan that I will have to press the brake, right? So automatically that means the planning must be there. So if a driver is not capable to plan the required motor action within a stipulated time, we say that this is the second kind of failure, which is called motor planning failure. Now, coming to the third kind of failure, which is the motor execution failure. Suppose a driver is visually alert, he has seen the changes in traffic signals as well, he has planned accordingly as well, but somehow he is very fatigued, he is very tired, and his muscle is not, supporting to this diver to actually execute the required motor action within a stipulated time. That means what happened? That means he has seen the changes in traffic signal, he has seen the pedestrian, he has planned accordingly within the stipulated time, but he failed to press the brake within the stipulated time. So if it is so, then we say that this particular failure is called motor execution failure, which is we can, term as, MEF, right? So these are the three kinds of failures we can talk about whenever we are talking about cognitive failure of any driver. Now coming to the problem, that whenever how we can solve this problem, a driver can have any of these three. So automatically whenever we design in that way that if a car is starting from this start position and a driver first experiences a visual attention failure, then it must be detected whether a driver is actually facing the visual attention failure or not. If yes, then one alarm must be generated. If no, then automatically we can understand that the driver is visually alert and he has seen all the changes in the traffic light. Suppose the traffic light is from green to yellow or yellow to red. That means he is supposed to press the brake, right? So if there is no visually attention failure, then what happens? Then we move to the second segment to determine whether the driver has been experiencing any kind of motor planning failure or not. Yes, I'm talking about an accident which has occurred. Then we are going to actually, searching the background that what kind of failure this driver has experienced this accident. So if he has not experienced any kind of visual attention failure, then we move to the second set of failure, which is nothing but motor planning failure. Again, we need to check whether the driver is going to experience the motor planning failure or not. If yes, then the alarm is generated. This is an automated alarm, and this alarm is generated within a stipulated time to actually, alert the driver so that he or she can be, escaped from the accidents to be occurred. But if there is no motor planning failure, then we should move forward and we should search for the third failure, that is motor execution failure. And whenever this motor execution failure is happened, if we can determine, then automatically the alarm 3 is generated automatically. And if no, then automatically we know that the driver is not experiencing right now any kind of failure. So whether the driving is continued or not. If yes, then this loop is going to be followed. And if the driving is not going to be continued, suppose we have reached or the driver has reached to his destination, then automatically he must feel to, stop the car, in naturally. So that is not due to any kind of accident or then any kind of, unnatural situation in the dynamic environment. So in that way, that driver, he or she needs to stop the car naturally and the car is stopped. Now the question is how we can determine all these failures and how we can combine these kind of failures with the brains, with the human brains, because in the previous slide we have shown you the human brain segments. So how we can collaborate this problem with the human brains as well as with the AI or ML. So for this, actually, now we are coming to discuss this particular slide where you can see that these brain signals, you can see that these are a kind of signals, right? These are kind of signals. So what are those signals? These signals, if you go and see the title, that title says that this is, EEG or EMG signals, which are the signals which are basically used in this problem. EEG is electroencephalography, that is the brain signals actually, which we can choose or we can select to actually determine this cognitive failure. How? Because every signal has its own nature. Every signal has its own feature. So what is feature? Feature is nothing but which actually describes this signal itself. So if we can extract or we can record our brain signals, and we are capable to extract certain significant features which are associated with the brain signals, then by determining or by analyzing those features, we can actually determine that whether a person is having any kind of failure or not. And for this, we need a certain classifier, or if in a natural way or a simple way, I can say that I need a detector. So I am coming to the detector part, after some minutes. First, I would like to, try to focus that what kind of features from the brain signals we need to extract or we need to focus so that we can extract significant features from these brain signals to address this cognitive failure detection in the driving problem. Apart from EEG, first I would like to draw your attention to another signals which is stated here, which is called EMG signals, which is called electromyographic signals, which is actually giving us the measure of muscle failure. That means whether a person is experiencing any kind of muscle failure or not, we can determine if we analyze the EMG signals. For this, actually, to determine any kind of failure from these two signals, we actually need to place the sensors on our body. Now the coming to the safety questions. Obviously, we are going to place the sensors non-invasive way. That means we are not going to any kind of invasive pattern. We are not going through the surgical process because there is certain ethical issues obviously. So for research purpose, we have certain portable or standalone EEG machines, right? Which actually, when we actually placed on the scalp of our head, it actually records certain brain signals. But these brain signals actually is generated much inside of our brain. So that is why it is having a very low order of magnitude, or I can say amplitude. It is actually in the order of microvolt. Just imagine how small it is. So that is why this EEG machine, either in the, either for the standalone machine or for the portable device, this EEG machine actually has its own EEG acquisition part as well as the amplification part. So that the small magnitudical, this brain signals are getting amplified so that we can extract the necessary features from the EEG signals. So this is the part of the EEG. Now coming from the EMG, again this is the electromyographic signals, and for this actually EMG sensors need to be placed on our arms. That means the arms of any driver, because he has to steer as well as on their foot because he has to press the brake or accelerator, right? So these are the sensors which we require to actually address this problem and to, identify or to, search for the solution as well. So now coming to the certain signal characteristics. So what are the signal characteristics, or what are the salient, EEG characteristics or EMG characteristics we need to look for addressing these kind of failure problem? If you can see here that we have mentioned that for visual attention failure, one P300 based detection is actually required. So now the question is, what is P300? What does this stand for? So basically, if you just look at the first picture, you can see that there is one signal on the top of this graph, and the bottom part is one onset of an audible visual or audio stimulus. Now the question is, what does this mean by audible? Those who are new in this AI, machine learning, and brain signals research domain, I would like to say that suppose during the driving, everybody, if I be a driver, if you be a driver, everybody of us actually are very much concentrate on the green signals, right? Because every time our in our conscious mind or in our subconscious mind, we will want to drive the car, right? We don't want to stop the car, and we don't want to wait for a longer time, right, at a particular point. So every time we need to run the car, we need to move the car. So automatically our consciousness is on the green light. So automatically in our subconscious mind, this green light is a very natural flow or natural color of the traffic signals, because we want to move the car. Now, what happens when suddenly red light appears? That means whenever... Is my screen visible?
Screen share. PPT, PPT, PPT.
Ma'am, it's not visible at my end. It was visible earlier, but now it's showing a blank screen.
Okay, okay.
PPT ta share करो. Screen share करो, PPT ta share.
Just a moment. I'm going to stop sharing, and again I'm going to share it, because at my end it is showing that my screen is shared. Just a minute.
Yes, ma'am, now it is visible.
Now it is visible? Okay, okay. Thank you so much. So for this, actually, this visual attention failure, actually what happened that we are talking about a kind of, green signal and the sudden change of the traffic signal from green light to red light, right? So automatically what happened, that means this sudden change of traffic light for green signals to red signals.
Madam, earlier it was visible. Now it's not visible at my end.
Now it is not visible?
Oh, it's visible from my side, madam.
Ma'am, it is visible.
Okay, okay,
It is
okay, thank you.
visible from my
Okay, thank you so much. Thank you so much. So, so automatically this sudden change in traffic light from green signal to
Ma'am,
red
it was
signal.
visible. Now I can see. After you have
Okay,
been shared.
okay, okay.
Sorry, ma'am. Can you please just repeat the last two lines, because we are
Yes,
not able to relate it with the presentation.
yes, yes, sure, sure. So I'm talking about the visual attention failure, which is the P300 based detection. So can you see my slide right now?
Yes, ma'am.
Okay, okay. Thank you so much. So we are talking about the sudden change in traffic signal from the green light to red light. So I'm talking about that whenever we are driving the car in our subconscious mind or consciously, we are actually trying to move the car, right? So in the subconscious mind, obviously, we are just looking for the green light. We are looking for the green light so that we can actually move. Right now, whenever the sudden change in the traffic signal occurs from green light to red light, so then this appearance of the red light in traffic signal, this is one oddball stimulus. And giving the example of oddball stimulus, as you can see that here is one mark which is saying that this is an onset of an audible visual or audio stimulus. So this is an example of audible visual stimulus. That means suddenly I am seeing that the traffic light changes from green to red. So whenever this kind of situation arises, that means whenever in the real life also, whenever any kind of audible stimulus, whether it is an auditory or it is an visual stimulus appears, then after this onset of this audible stimulus, almost after 300 milliseconds, in our brain, there is a positive deflection. There is a sharp rise of the positive deflection if you just see our EEG signals, you can see that there is, after 300 milliseconds from the onset of this stimulus, there is a sharp rise. And since this is a positive rise or positive deflection, we are saying this is P. And since this is actually happening or occurring after 300 milliseconds from the onset of the stimulus, that is why we are saying this is the P300. So this is one specific, brain signal characteristics which we actually, incorporate in our problem in the cognitive failure detection, because a driver has to be determined whether he or she is experiencing any kind of visual attention failure or not. That means if I get any kind of P300 signals from the onset of the change in traffic signal, I can easily conclude that yes, this driver is visually alert. And if I find not, then automatically I can actually comment that this driver is not visually alert. Maybe he is unmindful. So this is one particular brain signal characteristics. Now coming to the second one, the middle one. See, this particular characteristics, which is called ERD-ERS based detection, that means event related desynchronization, followed by event-related synchronization-based detection, which actually determines whether a driver is having a motor planning failure or not. So for this, actually, what is the characteristics of the brain signals? So this is actually related to the motor planning. That means whenever a driver is imagining or whenever a driver is starting its planning to actually execute certain motor, operation or motor action for the sudden change in dynamic environment or sudden change in traffic light or sudden arrival of pedestrian. So whenever the imagination is started to actually generate or to actually execute a certain motor operation, after almost 550 milliseconds, you can see a sharp fall in the brain signals, which is called event-related desynchronization. That means the brain signals is getting desynchronized from the original signal magnitude, right? And after that means this is the whenever the planning is started and whenever the planning is stopped, because automatically we human beings also need a certain very minimum amount of time to plan, right? Because our mind is so fast. So automatically whenever our imagination or that is imagination to execute any kind of motor planning or the actual motor execution also, whenever we are actually stop that particular imagination or execution, then automatically you can see in the brain signals that there is again a rise in that signal, and this signal you can see that again tries to match with the original signal amplitude. So this is called event-related synchronization. That means now the signal is trying to synchronize with the original signal, amplitude before the onset of the motor planning or motor execution. So that is why whenever we have not seen these kind of, signal characteristics, after the change in traffic light, after the sudden arrival of pedestrian or something like that, then we can say that the driver is not very much, attentive, or the driver cannot be able to plan required motor action within a stipulated time. So we can say that this is the motor planning failure has occurred. Now coming to the third one, which is specifically depends on the EMG based detection. That means whenever we have not, received any kind of, this kind of, positive deflection, whenever we are actually steer our steering wheel in the left side or in the right side, automatically certain muscle action is required, right? So whenever we have this kind of muscle action, or whenever we are, just pressing our brakes or pressing our accelerator, then also we need a certain, muscle action near our foot area. So the EMG sensors placed on the arms, wrist and the foot actually, captures those muscle actions, and it actually gives you the kind of, this positive deflection, which actually ensures that yes, you have performed your motor actions correctly. So if we have not received this kind of, deviation again, so we can conclude that yes, the driver cannot be able to execute the certain motor, action. So automatically EMG based detection, determines that whether a driver is experiencing the motor execution failure or not. So this is how we can, address each one of these kind of, failure. So now the coming to the point that whenever we have already, decided, or we have understood that these are the salient characteristics of the brain signals or the, electromyographic signals. So now the question is that what kind of, features or what kind of, characteristics we are looking for from the brain signals and from the EMG signals. So now this slide depicts you that how this P300 based visual attention failure detection actually occurs. So here we relate from the real world, scenario that we have performed, which actually the experiment we have performed in artificial intelligence lab of Jadavpur University, Kolkata, where actually we have one driving simulator, and we just showing you one picture of car, which is actually giving you the sense of that a driving simulator is working. And suppose a driver is driving his car, and this driver is actually under the, experimenting environment, where actually his brain signals are recorded from frontal area. This F stands for frontal lobe. This frontal area, this prefrontal area, that is this region, and the parietal area, that means the parietal lobe, which is this kind of region. So frontal, prefrontal and parietal. So electrodes, EEG electrodes are placed over these three areas, and EEG signals or brain signals are collected during these frame of time, where you can see a kind of, sudden change in dynamic environment. As you can see here, sudden obstacle, let's say, is coming, on his way. So what happens here? So obviously this driving involves the sensory perception. Here we are focusing about the visual perception. If we want to, determine whether this driver is experiencing any kind of visual attention failure or not. So for this, we need to identify whether this P300 occurs or not from his EEG response. And EEG response is going to be collected from all these three areas. So if the P300 is, visible, then after almost 300 milliseconds from the onset of the stimulus, so this stimulus is nothing but this obstacle here. So automatically, if this is, visible, if this is appearing, then we are very much, calm state of mind, because we can comment that this driver is visually attentive, and visually it can sense any kind of obstacle in the dynamic environment, and he is not experiencing any kind of visual attention failure. But what if there is no P300 generation? Then automatically we can now able to comment that yes, this driver is having the visual attention failure, and in that case one alarm is going to be generated. Now, what are the artificial intelligence or machine learning techniques we are going to incorporate with this real world problem? That is, we are now going to, record the brain signals during these, phase of time. And since this is a raw signal, so we know that however we are saying that we are trying to focus anything, we are trying to focus on certain driving, but still, since this is a human mind, still we experience that our mind somehow, sometimes may be engaged into some secondary thoughts, right? So automatically that secondary thoughts is not related to driving or not related to focusing the change in traffic signal, the change to actually to observe, visually to observe or to be visually alert to actually identify whether there is any change in traffic light. That is basically our primary job or primary thoughts, but the secondary thoughts is something else, and these secondary thoughts are actually treated as noise. So what we need to do, we need to filter those noise. We need to filter those noise so that we can we can get or we can receive the cleaned EEG signals from the raw EEG signals. So that is why we are going to do the filter. Now filtering in any kind of, any kind of literature also, if you go through, you can see that this term is also called as pre-processing. Why it's called pre-processing? That means not only the secondary thoughts as well, some kinds of, artifacts must be there which needs to be removed. Some kind of artifacts means some kind of, blinking artifacts. See, whenever I'm talking to you, still this is a very natural phenomena which I cannot, control. So these are kind of, blinking eye blinking is a kind of artifact which also needs to remove, because that is also, adding some kind of noise in our actual, brain signals, which is just only responsible to determine the visual attention failure. So for that, we are going to take a certain band pass filter. Now, how to select this, pass band of this band pass signal, how to select the lower frequency, lower pass band or the upper pass band, that depends on certain kind of brain signal rhythms. We have a certain kind of brain signal rhythms like mu rhythms or alpha rhythms, beta rhythms, theta rhythms. So these are the some kind of, rhythms or gamma rhythms. So all these rhythms have a certain, band gaps. So automatically, depending on what kind of, rhythms, brain signals or brain rhythms we are trying to capture, that is, where actually we can find these P300 signals. So depend on that, we are going to, select the pass band of the filtering. Now, the selection of this passband actually, is depends on the more and more the extensive, expertise in this research domain and the literature survey, and also due to some kind of, natural, that knowledge or natural this kind of sense. So here we have taken the alpha band, which is basically, associated with the alertness. So visual alertness detection needs a kind of, filter which has a band pass filter, which actually allows the alpha band. So this is the 7 to 13 hertz is the frequency band of this particular alpha rhythm. So we are going to filter those part of the brain signals. Now, once we have got this particular brain signals, now coming to identify the features or extract the features. As I have already told you, that feature is something which is very significant to its signal itself. That means automatically, if you can now, see me, so you can automatically, for the last, half an hour or so, you can actually, identify that I have certain features. So that is my features, right? So this is, in that very case, the signal is also having a certain features. So if we extract the EEG signals, EEG features from this clean EEG signals, then processing those features, we can easily detect whether we have got this kind of P300 or not. So for this, we need some feature extraction techniques. So this is one part of the artificial intelligence and machine learning technique where you can get, there are several feature extraction technique which is associated with the brain signal interface or brain computer interface, which is artificial, which can be very much useful to actually give the salient or significant features to any kind of classifier to detect any kind of failures. So what are those? There, the list is very much big. What are those features? The features like, for example, that is power spectral density. There is another feature which is called discrete wavelet techniques. There is any kind of features that is adaptive autoregressive features. So here AAR feature is the adaptive autoregressive features which we have taken, which is very much important and very much useful to actually identify very much time-stamped signals, time-stamped any kind of change in the signals. So that is why this kind of feature extraction techniques we have chosen. If you have asked that, ma'am, how can I identify that this particular feature extraction gives me the better result, you can go for that reason, you can go for several standard feature extraction techniques like power spectral density, like discrete wavelet transform, like adaptive autoregressive parameter, like Zorth parameter, or like entropy. There are many such time domain or spatial domain or time frequency related domain correlated domain features are available. So you can go for a list of features and then you just apply those feature extraction techniques on your clean EEG signal so that all the features are going to be extracted, and then you need to feed those features to the classifier. Now, this is something which is very important in any artificial intelligence or machine learning related problems, that we have to design a particular classifier, or we can go for any standard classifier or traditional classifier, which can help to detect whether we have, experienced or our driver has experienced any kind of failure or not. So now I would like to take a few minutes to actually explain that how does this classifier classifies. That means from the name itself, you can actually, have an idea that a classifier classifies means if I have a certain kind of, a bunch of red tomatoes, and if I have a bunch of, a certain kind of, certain tomatoes which are not so ripe, that's a raw kind of a certain kind of greenish one. And if I just mix all those tomatoes, and if I just tell you that to just segregate all those two types of tomatoes, then you can easily classify those red tomatoes from the greenish kind of tomatoes. So this is how exactly classifier does. That means if you just go on just remembering with that, whenever we were kid, so how our parents have utilized their time, their effort, their sincerities, so that we can learn new things. That means we can learn to segregate things, right? We can learn to segregate red boxes from green boxes, right? So there, the classifier also does this kind of things. So for classifier, we can have two kinds of classifier. That means this classification techniques, classifier actually classifies something with the help of an algorithm which is called a classification algorithm. Now, based on this classification algorithm, we can have two kinds of classifier. One is supervised classifier, another is unsupervised classifier. So whenever we have unsupervised classifier, when we are talking about unsupervised classifier or unsupervised classification algorithm, that means we are actually, telling that there is no certain kind of supervision is there. There is no presence of supervision. That means the classifier classifier tries to segregate these red tomatoes from these green tomatoes by its own knowledge. That means, yes, this is looking like a reddish one, so I will keep here. So this is looking like a greenish one, so I will keep aside here. But nobody is telling this classifier, or no supervisor is instructing this classifier that yes, this tomato is a green one. That means no labeling is there. So whenever there is no labeling, we are saying that this classification algorithm or this classifier is basically the unsupervised classifier or unsupervised classification. Okay. Still, I am having some time. Okay. I am just taking a few minutes, and since I cannot, observe the timer here, so I would request the assistance panel that whenever the time is approaching 8 or by 8, they should please, inform me or intimate me. Okay. Thank you. So in this way, actually, we are actually the unsupervised classification algorithm actually classifies in this manner. So what happens whenever we are going to, shift from unsupervised classification from supervised classification? Then what happens that here actually you can see that one particular, terminology has been written, that is which is called KSVM classification. So KSVM classification is a supervised classification. That means this SVM means this is support vector machine. This is one kind of supervised, very popular and very useful supervised classification technique. And this K stands for kernel. That means kernel-based support vector machine classifier is used, which is a supervised one. So now the point is, whenever we are applying a supervised classification or algorithm or supervised classifier, how does this classifier works? So this classifier actually, is fed with some training data. That means I have given just, a couple of minutes before, I have given you one example of red tomatoes and some kind of greenish tomato. So actually, each and every tomato should be labeled for this supervised classification. And if now we are going to feed this one tomato, let's say, to the supervised classifier, where along with one label that yes, this is a red one and it belongs to class 0, let's say. So that means the classifier is now learning that yes, I am getting a red tomato and this actually belongs to class 0. Fine. So it is the learning. That means we can also say that this is a training phase of the classifier. That means the supervised classifier. So you can see that there is one supervisor here. There is a sense of supervision involved here, which actually tags the class level of a particular data point, right? So here the data point belongs to our brain signals, right? Our raw brain signals. After then this is filtered one, and then the features are extracted. So automatically those features are nothing but some ASCII values, some data points, which is actually associated with some brain signals, right? So now, if this is a one kind of, one particular red tomato, then again for the next red tomato, again the classifier needs to learn that yes, I am getting another red tomato, and yes, this is also belongs to, class 0. So in that manner, classifier learns all the red tomatoes which belongs to class 0. Now coming to the, obviously we have a mixture of red tomatoes and the slightly greenish tomatoes. So whenever we are feeding this particular, greenish tomato as well to the classifier, someone please mute. Someone please mute. Yes, thank you. So automatically, so whenever the classifier gets the greenish tomato, then automatically he senses that it is not going to belongs to the class 0. And how? Because this greenish tomato is also coming with a tag or coming with a class level, which is saying that yes, this tomato belongs to class 1, but not from the class 0. So automatically all the greenish tomatoes are also fed to the, classifier, supervised classifier, along with the class level that yes, all the greenish tomatoes belongs to class 1. Now what happened that out of this all mixture, there are certain amount of red tomatoes and green tomatoes we have kept aside. Okay. And the remaining portion, the remaining major portion, we have fed to the classifier, supervised classifier. Now, based on that particular, training instances, this support vector machine algorithm or this support vector machine classifier actually tries to draw or tries to create a hyperplane. Hyperplane means if I'm just giving you one example, that if I instruct you that you need to just segregate one red box from all the green box, see, automatically you just keep all the red boxes at one side and you just keep the green boxes at the another side. So automatically you can see that there is one region, right, where you are not going to put any red boxes or any green boxes. So a kind of sense of, partition, a sense of, we can say, a particular plane, hyperplane is going to be formed. But what happened whenever we have more and more larger data points, and some data points are kind of, that I have given you one example of this red tomato and greenish tomato, right? What if one tomato is half a kind of, raw or half kind of ripe? So there comes the logic of the fuzziness. That means this is a certain kind of, greenish one, certain kind of, reddish one, but we cannot actually label it as this is the greenish one or this is the reddish one. So somewhere you can see that these particular tomato falls within the falls within the hyperplane, right? So within the close vicinity of this mid plane or this hyperplane. So whenever this hyperplane is being formed for this support vector machine classifier, this training of this classifier is done. Now coming to the testing part. So for this testing part, what we require to feed to the classifier, those small segments of the red tomatoes and the greenish tomatoes which we have kept aside. Now we are going to feed one by one without any label. That means now we are not going to, dictate that classifier that whether this tomato belongs to the greenish one or belongs to the reddish one. Somebody please mute your mic. Fatima Chandini, please ma'am, mute your mic.
Ma'am, please unmute yourself.
Am I audible now?
Yes, ma'am.
Okay. So for that reason, whenever we are going to, sending this red tomato and this slightly greenish tomato from our testing data points, then we are not actually, labeling the class labels with all these training data sets. So automatically what happens, these are called the testing data points because we are not going to tag any class level with any of the tomatoes. So what happened that whenever we are sending these kind of, testing instances to the classifier, now we are letting this classifier to determine whether this classifier finds a similarity of a particular testing instance to whatever the learning instances or the training instances it has stored earlier. Where does the similarity? Is the similarity with the class 0 tomato, or is the similarity with the class 1 tomato groups? So based on that similarity metric, actually this classifier classifies any of these two classes. Either this tomato is going to be detected that it belongs to class 0 or it belongs to class 1, but depends on that similarity matrix. That means this classifier is going to match the features of this testing instance with the features of the training instance it has already learned. So this is how a supervised classifier actually works. And here also this kernel-based support vector machine classification is also works. So here in this particular visual attention failure detection, what are those two classes for classifier to detect? One is either the driver is visually alert, and another is either the driver is visually non-alert. So that is why you can see that the classifier, classifies all the, extracted features in either of these two classes. That means either the driver is alert or the driver is non-alert. Clear? So this was now the visual attention failure technique, where you can see that there is a control if there is no P300 detected, and if the classifier detects that the driver is visually non-alert, then automatically the control is going to be taken automatically in the alarm generation part. So automatically alarm is going to be generated so that the driver is going to be alert that yes, he needs to, observe certain, changes which has already occurred in the dynamic environment. So now it is coming to the ERD, ERS based motor planning failure detection. So see, in the similar pattern, now we have already understood that this is event related desynchronization followed by event related synchronization. Brain signals are actually responsible to determine this motor planning failure, right? So for this, actually from the same EEG sensors, but we have to collect the EEG signals from some different locations. So what are the locations? Locations is from some kind of, the common part, which is the parietal one. And there is one part, which is the motor cortex part, which is basically, plays the significant role in motor action, right? So once we have again recorded, this particular EEG signals, we are going to filter it out. We are going to extract the certain features using the, that significant and the useful, features extraction techniques, obviously based on certain literature survey and the extensive, experimentation. So after this feature extraction technique, we have again, found out certain, features which are very, very relevant to determine the motor planning failure. And again, we are actually sending the classifier to actually classify whether the driver is being able to plan to, accelerate, to brake, or to steer right or left, or no action. So actually here, if you just see from the last slide, in the visual attention failure detection, our class was only 2. Now we have enhanced our classes as well. So automatically the classification is getting more challenging. So for this, we are going to introduce certain classifier, which is the fuzzy classifier, and also type 2 fuzzy classifier. Now there lies a novelty that why we are actually incorporating this fuzzy classifier, because you see this motor planning this phenomenon, this particular action needs a very precise, planning, because, to actually, whenever we are at particular, changing lane position, so automatically, within very stipulated time, we need to actually plan that whether we are going to steer left or steer right. If we can, perform, if we have performed a little bit wrong, then automatically a fatal accident may occur. And also somehow there, since that particular, this is going to be challenging, because we are actually dealing with four different kinds of motor planning within a very small, stipulated time, that whether we are going to, accelerate, whether we are going to brake, that is also, in real time, that is the, functionality of our both legs, right, the left legs, right legs, and we have to actually, release the brake pedal once and then accelerate, or accelerate pedal we are going to release and then press the brake pedal. So this is a very, complex situation, and that particular complex planning we need to perform within a very stipulated time, and that is why there is a certain kind of vagueness, certain kind of, confusion can be occurred. So there is a possibility. Since there is a possibility to, evolve this kind of, confusion or complex scenario, we actually move for the fuzzy classification. But for this, you can see that there is one another building block we have incorporated. What is that? Because since till the last slide, we have understood that any brain computer interfaces has certain basic steps. That is, one is brain signal acquisition. Then we have to pre-process or artifact removal through the filtering technique. Then we have to extract certain features. Then automatically we are going to send these EEG features to the classifier. But what is this? This is called feature selection. Now, why this feature selection step is required? This feature selection step is required whenever we have large feature set, and also the large feature set, in this large feature set, which belongs to different classes. And if there is a certain kind of vagueness or certain kind of, what should I say, certain kind of commonness, then we need to extract most significant feature from a large pool of selected features. That means initially at the first step, we have extracted the brain signals, that means EEG features from the brain signals itself. Then at the second step, again, we need to reduce the size of the feature set if our feature size is too long. And also we have seen that there is a very commonality between the features which is belonging from the different classes. Then we incorporate another steps which is called the feature selection steps. And there actually for feature selection we can incorporate any of these kind of artificial intelligence or machine learning algorithms, like differential evolution, or like genetic algorithm, or like particle swarm optimization. But obviously each and every technique has its own limitation, his own benefits. So depending on that, we need to choose for a particular, efficient and effective the feature selection techniques, which is actually suitable for our given problem. And the selected significant features are now ready to feed the fuzzy classification. So now this fuzzy classifier actually, classifies the four motor planning operation, that is in the four different classes that you can see, that ACC is the acceleration, braking, steering control, or no operation. So this is how the extracted features look like. If you go on the real time, research work, then you can see that we have already, collected the raw EEG data and then we have filtered one. So you can see the some kind of, visually inattentive EEG data from the visually attentive EEG data, where actually, this oddball stimulus occurs, and after almost the, this P300 milliseconds time, actually, you can see a sharp edge, which is a positive deflection, which actually gives you or ensures you the presence of this P300 deflection. That means if you have this P300, you can now, all of us are now able to comment that yes, this driver is visually attentive. So this is the visually attentive EEG data, we can say. And here you can see that there is no such, positive rise after almost 300 milliseconds. So we can say that this is the visually inattentive EEG data. So after when we have brought out this raw EEG data, and we have this filtered EEG data also. This is the filtered EEG data from the motor cortex electrode for any kind of, stimulus type. That means there are 4 kinds of, traffic light changes instances. And if you just go through, you can see that there is a, filtered EEG data. Now you can see here that this x-axis is actually the frequency in hertz, and this y-axis is actually the EEG amplitude. So this is the frequency in hertz, and you can see that this C3, this motor cortex, is actually, very much responsible to address the beta rhythm of our brain signals. So this beta rhythm is having the, frequency bands of ranges from the 13 hertz to 30 hertz. So you can see that whenever we are going to filter this motor cortex brain signals, we are actually getting the signals by filtering all those raw signals with a band pass filter having the pass band of this 13 hertz to 30 hertz. So this is somehow the filtered EEG signals. And you can see whenever we are applying any artificial intelligence or machine learning techniques for feature extraction methods to extract the salient and the significant, most prominent EEG features. So you can see that if I see the power spectral density, which is a very prominent one, so you can see that this PSD feature extracted from EEG during acceleration or braking or steering left and steering right. So for these 4 kind of motor planning operation, you can see that we have received the, different power spectral density as well. But automatically those are very significant one, because if you just go on through the PSD feature values, you can see that it is getting like, from 75 to up to 600 also, right? But you can see that during acceleration, actually the PSD features or power spectral density is found the highest one, right? So if you just want to go through the, the research work which we have performed in Jadavpur University in artificial intelligence lab, then you can go through this paper also, which is published in IEEE Transaction on Emerging Topics in Computational Intelligence. And you can see that there we have, incorporated, there are certain ways so that we can actually finally determine all the 3 failures of the driver during the driving. Okay, so this is 8:10, and probably our next resource person is there. Can anyone guide me that whether he is present or not? Then I will stop sharing.
Yes, yeah, he's present. I think so.
Okay.
Yeah, jumped.
Okay. So, okay, then I am going to stop sharing, and I am just asking to the participants if they have any query or is understandable from your side, and how you are,
এইটা না আমার মাথা থেকে
feeling,
শুধু বেরিয়ে যায় পার্টিসিপেট
how you are understanding. So anyone has any
Shah, first of all, I would
query?
like to thank you for the wonderful presentation and for this lucid illustration of such remarkable breakthrough of our technology, that is BCI, which is used in this, one of the most significant problems of India, that is drunk truck drivers at night, and
Yes.
where you study the brain signals of such kind of drivers using such non-invasive techniques like electroencephalography. So obviously it's a breakthrough, breakthrough technology as well as remarkable research. So I strongly believe that all the participants have thoroughly enjoyed, and they must be having many queries on this ongoing research. But as the time is limited, obviously I cannot accept all the questions from the audience, but of course I should be addressing a few from you. So participants, I will be glad if you share your doubts or queries with Dr. Saha right now. We will have a 5 minutes short question answer session here right now, because our next resource person is already here and we are all eager to listen from him. So participants, if you have any query, we can have a quick review of that, please. Question from the audience? Any question from the participants, please? I think they need much time to digest everything, because there are so many things assembled in this research: machine learning, AI techniques, signal processing, electronics measurements, instrumentation. So it's obviously an overall a very, what should I say, significant research, ongoing research. We need to go through it in a very calm and cool mind. So thanks, Dr. Shahal, for giving us the glimpse of such kind of research, and we are eagerly looking forward to listen from you on this in a more broadened way in near future.
Thank you so much. Thank you so much.
Thank you,
So
Dr.
I
Shahal. So we should take a 5 minutes break or as we are lacking time, so we can just come back after 2 minutes.
okay, sure.
Okay, participants. So we are just taking a very short break for certain arrangement of recording as per AICTE ATAL FDP rules. So after that, we will quickly resume the session with our next resource person.
For one thing I would like to say that due to ATAL scheme, actually ATAL guidelines, we need to take the screenshots of every session participants. So I would like to request all of you to just to just share your screen or share your camera, actually, to just enable your camera for 2 to 3 minutes so that we can take the screenshots, which is actually going to be attached with the attendance, and we have to upload in the portal also. For only 2 to 3 minutes. Yes. Thank you so much. Now you can turn off your camera. Okay, so we are having a 2 to 3 minutes break right now. And one thing I would like to address here, that is from coordinator side, it is my responsibility to address you that in all the session, whatever we are going to conduct, the attendance is mandatory. And once you have completed one session, you just be alert in your WhatsApp group, because one feedback link is going to be provided in WhatsApp group, so that you are going to fill up those feedback links, and that is the Google form itself. So you have to fill up those Google forms and upload it. Okay, then you submit it. Every day except the Saturday, you will have 2 sessions in a day. So for 2 sessions, you will have to submit your Google form within 12 a.m. at night. That means before 12 a.m., you will have to submit the daily attendance of the 2 sessions. But for Saturday, you will have the 3 sessions. So automatically 3 Google Forms, the 3 links for the 3 Google Forms, separate Google Forms, you are going to, fill up. And for this, in your WhatsApp group, in very short time, you are going to receive one particular list where you can find your names, your email ID, and also one faculty ID. That means the FDP ID from our side. Okay. So whenever you are going to, fill up the feedback form, just be and ensure that you are going to fill up your name by which you have been you have registered in this ATAL FDP, not any another name, because that is the name you have already registered in the ATAL portal. So your if there in AICTE, if there is some mismatch in the attendance in the Google, in the feedback form, and in your name which is actually registered there, so if there is a mismatch, there may be a problem in generation of the certificate. So I would like to request you to please fill up carefully with your name, which is actually the registered one, and also include or also fill up your FDP faculty ID, which is which is found in the PDF file, which I'm going to just share within a few minutes. Okay. If you have any queries, you can ask. Okay, then. Okay, then. So I'm going to leave right now, and I will request my co-coordinator, Dr. Pratusha, to introduce our next resource person, Dr. Parijat Bhomik.
So dear participants, I hope that you enjoyed the very first session, and we are waiting here with the next exciting session from our very beloved, respected Dr. Parijat Bhomik. So